Have you at any point inspected whether we're genuinely alone in the universe or thought about how conceivable it is that there's more to our reality than what we see? Envision, in the event that the James Webb Telescope at last uncovers that we live inside a dark opening. Such a revelation could rethink how we might interpret the universe and force us to reevaluate all that we assumed we knew. So, what precisely are dark openings? They're like something out of a bad dream. Sure, you might have seen them in science fiction motion pictures, but in reality, they're genuinely unnerving. According to researchers, dark openings in space are believed to contain gigantic measures of matter packed into an incredibly small region. Envision a star, much larger than the sun, condensed into a sphere the size of New York City. The gravitational pull is so strong that nothing, not even light, can escape. Researchers have been captivated by dark openings for quite a long time. They've studied objects in space so enormous and dense that they trap light. The most unmistakable theories about dark holes stem from Einstein's theory of general relativity. Basically, when a massive star collapses, it leaves behind a dense core. If the mass of this core is several times that of the sun, gravity overpowers everything, creating a dark opening. Identifying dark openings is difficult since they emit no light. However, researchers have found ways to infer their presence by observing their effects on nearby matter. For example, if a dark opening passes through a cloud of interstellar matter, it pulls that matter toward it in a process called accretion. Moreover, when a star gets too close to a dark opening, it can be destroyed, emitting X-rays in the process. Dark openings also significantly affect their surroundings. They can consume nearby stars, emit powerful radiation, and even influence the formation of new stars in some regions while slowing it down in others. But where do dark openings come from? Envision stars, once massive and powerful, meeting their end in a grand event called a supernova. From the remnants of these fallen giants, dark openings emerge. Most dark openings are born from massive stars that end in a supernova explosion. Smaller stars, when they die, become neutron stars, extremely dense but not dense enough to trap light. However, if a star's mass is several times that of our sun, it collapses under its own gravitational force, forming a dark opening. As these collapses occur, something unusual happens near their surfaces. Time itself begins to warp. From the perspective of someone far away, time appears to slow down near the event horizon, the point of no return for anything falling into a dark opening. Sometimes, when two smaller dark openings collide, they merge into a larger and more formidable dark opening. If a dark opening interacts with a neutron star, they create a massive phenomenon that challenges understanding. Researchers have grappled with the size and nature of these massive entities for a long time. Dark openings come in two primary sizes, stellar and supermassive. But even small is relative when it comes to dark openings. Stellar mass dark openings, the remnants of giant stars, can be 10 to 20 times the size of the sun. There may be as many as 10 million to a billion of these in the Milky Way alone. However, even these pale in comparison to supermassive dark openings, which are millions or even billions of times larger than the sun. These titanic entities reside at the centers of massive galaxies, including our own Milky Way, acting as enormous gravitational anchors. The eminent physicist Stephen Hawking studied dark openings extensively. His discussions were always captivating, though some of his theories remained unproven due to a lack of suitable equipment. However, hope is on the horizon thanks to a groundbreaking scientific instrument, the James Webb Space Telescope, JWST. The JWST is no ordinary telescope. It's an engineering marvel and a testament to human creativity. While past space telescopes like Hubble have served us well, the JWST is in a class of its own. With a staggering price tag of $10 billion, this extraordinary instrument was brought to life through the collaborative efforts of NASA, the European Space Agency, and the Canadian Space Agency, along with contributions from over 300 universities. Despite the risks associated with such an ambitious project, the JWST has already exceeded expectations. After a successful launch, NASA announced that the telescope has enough fuel to last more than twice its initial mission life. The telescope has traveled over 1 million miles to reach its orbit around the Sun, where it will remain indefinitely. Along its journey, it successfully deployed its massive 5-layer sun shield and giant primary mirror, both of which had to be folded to fit inside the launch vehicle. After careful calibration, the telescope is now nearly ready for full operation. One of its most exciting achievements came when NASA announced that it had captured its first images of starlight. The first image of a star, called HD 8446, resulted in a mosaic of 18 scattered bright spots, representing the light captured by the 18 mirror segments of the primary mirror. NASA later released another stunning image in which the 18 images were combined into a precise hexagonal arrangement. Thanks to its advanced technology, the JWST will allow researchers to study the earliest stages of the universe after the Big Bang. It will focus on the formation of the first stars during the epoch of reionization, a period when neutral hydrogen was reionized by radiation from these stars. This involves looking back billions of years, an accomplishment only possible with a powerful telescope like the JWST. The telescope will also support the search for exoplanets, which are challenging to detect due to their interaction with their host stars. Its sensitive instruments can observe these planets more closely, even analyzing their atmospheres. Understanding the conditions of these planets could help researchers determine if they are habitable. Additionally, scientists are using the JWST to study galaxies, aiming to understand how matter is organized on a large scale and how the universe evolved. By examining the earliest galaxies, researchers hope to uncover how they formed and developed into the structures we see today. Above all, the James Webb Space Telescope may help answer some of humanity's biggest questions. Are we alone in the universe? Are we living inside a dark hole? The JWST has already started its hunt for answers, and its findings are nothing short of extraordinary. Recently, it discovered compounds called polycyclic aromatic hydrocarbons, PAHs, surrounding very massive dark openings in 3 active galaxies. These carbon-based molecules, with their unique ring-like structures, are significant for several reasons. Not only could they serve as the building blocks of life, but they also help astronomers track star formation. When ultraviolet radiation strikes these PAHs, they emit infrared light, a signal detectable by the JWST's mid-infrared instrument, MIRI. This signal often indicates the presence of young, hot stars nearby. However, here's the twist. The JWST identified these molecules in regions where the extreme gravitational forces of dark openings were expected to destroy them. This unexpected discovery raises fascinating questions about the interaction between dark openings and the molecular building blocks of life. What's even more intriguing is that the JWST isn't just helping us understand dark openings and their surroundings. It's also revolutionizing our knowledge of planetary systems. By observing distant exoplanets, the telescope has detected key atmospheric components like water vapor, methane, and carbon dioxide. These findings could help scientists identify planets with conditions suitable for life, narrowing the search for extraterrestrial life forms. But the JWST's capabilities don't stop there. It is also designed to study the mysterious dark matter and dark energy that make up a significant portion of the universe. By analyzing the distribution of galaxies and their movements, researchers hope to uncover the role of these invisible forces in shaping the cosmos. One of the most mind-bending questions the JWST aims to address is whether we are living inside a dark hole. This radical theory, proposed by some physicists, suggests that our universe could be the interior of a massive dark hole in a higher dimensional space. While this idea may sound like science fiction, the JWST's ability to peer deeper into the fabric of space-time could provide evidence to support or disprove this hypothesis. As the JWST continues its mission, it's clear that we are on the brink of groundbreaking discoveries. The data it gathers will not only expand our understanding of dark openings, galaxies, and planetary systems, but also challenge our perception of existence itself. The universe is tremendously strange and loaded with shocks, hanging tight for us to reveal its privileged insights. Inquisitive astrophysicist Ismael Garcia Bernard from Oxford School chose to focus on three unique frameworks known as NGC 6552, NGC 70319, and the notable Stefan quintet found countless light years away in the profundities of dimness. What Garcia Bernard discovered will make your hair stand on end. In the central localities where dark holes rule, he found a lot of PHS. Sounds interesting, right? Well, here's where it gets chilling. The radiation near those huge dark holes bent the PHS, essentially changing them into larger, electrically neutral adaptations of themselves. The more humble, electrically charged PHS disappeared into the significant dimness. Imagine being consumed by the real lack of clarity. Yet, stand by, there's a promise of something better. Or maybe not. The authentic question here isn't whether we're alive, but whether we truly exist. Does everything around us exist because of the dark hole we're in? Everything seems to align with a theory that perhaps we're not simply living inside a dark hole, but instead inside the event horizon, a boundary between the universe we know and the unknown. Could it be that everything is connected inside a dark hole? The James Webb Space Telescope is out there right now, searching for answers to the unknown. Stay tuned, and perhaps it will make us all rethink what we assumed we understood about existence. Reality may be far more warped than we realize. In the enthralling universe of cosmology, few subjects have generated as much interest and mystery as dark holes. These colossal entities, with their ability to twist space-time and consume everything in their vicinity, have long been the subject of both scientific study and popular imagination. The discovery that we may have finally found what's inside a dark hole, made by eminent physicist Michio Kaku, intensifies the wonder and intrigue surrounding these puzzling objects. But what does this bold statement mean? Has science finally unlocked the mysteries of what exists inside the event horizon of a dark hole? To understand Kaku's explanation, we need to step back and examine the concept of dark holes, the current state of research, and the significance of the latest discoveries in the field. A dark hole is a region in space where the gravitational force is so strong that not even light can escape. This phenomenon results from a massive star collapsing under its own gravity after depleting its nuclear fuel. When this happens, the star's core contracts, and if the mass is great enough, it forms a singularity, a point of infinite density where the laws of physics, as we know them, break down. Surrounding this singularity is the event horizon, the boundary beyond which nothing can escape, not even light. For a long time, the existence of dark holes was purely theoretical. The concept first emerged from Albert Einstein's general theory of relativity. However, it wasn't until the 1960s and 1970s that scientists like John Wheeler, Roger Penrose, and Stephen Hawking developed the mathematical framework that brought dark holes into the realm of accepted science. Even with this theoretical understanding, dark holes remain shrouded in mystery and speculation. What happens beyond the event horizon? Is it possible to peer into the interior of a dark hole, or is it entirely inaccessible? The event horizon represents a limit beyond which there is no return. When something crosses this boundary, it is inevitably drawn toward the singularity at the center of the dark hole, where it is crushed to infinite density. Despite their prominence in the dark hole model, the event horizon is not something we can directly observe. The very nature of a dark hole means that light cannot escape its gravitational pull, making the study of what lies beyond the event horizon incredibly challenging. For decades, dark holes were considered cosmic prisons where information about the objects falling into them would be lost forever. This idea was epitomized by the so-called information paradox, which arose from Stephen Hawking's work in the 1970s. Hawking proposed that dark holes could gradually evaporate due to a process known as Hawking radiation, a quantum phenomenon implying that dark holes slowly lose mass over time. If this radiation carried away all the information about what had fallen into the dark hole, it would violate a fundamental principle of quantum mechanics, known as unitarity, which states that information must be preserved. As the field of dark hole research continues to evolve, new questions and theories emerge, challenging our understanding of the universe. One such intriguing concept is the idea that dark holes could serve as portals to other parts of the universe, or even different dimensions. This idea is rooted in the concept of wormholes, hypothetical passages that could connect distant regions of space-time. While wormholes have not been proven to exist, they are often depicted in science fiction as shortcuts across the universe. If these exotic objects were real, they could potentially provide a way to bypass the vast distances between universes, offering a glimpse into an entirely different realm of space-time. Moreover, dark holes have sparked discussions about the very nature of reality itself. Could it be that the universe we perceive is a simulation or a construct within the event horizon of a dark hole? Some scientists and philosophers have suggested that the nature of our reality might be tied to the mysterious forces governing dark holes. These questions prompt us to reconsider the fundamental principles of physics and the role of consciousness in our understanding of the universe. Could we be living inside a dark hole, surrounded by distorted space-time that alters our perception of reality? Interestingly, dark holes could also provide insights into the nature of time. Objects near the event horizon experience time dilation. The flow of time slows down relative to an observer far away. This curious phenomenon could hold the key to understanding the flow of time itself, and whether time is continuous or something that can be manipulated by the forces at play in the universe. Research into dark holes may one day unveil new technologies or theories that allow us to manipulate time or even travel into the past. In the end, dark holes may be the universe's ultimate mystery, and the James Webb Space Telescope, with its cutting-edge technology, could play a crucial role in uncovering their deepest secrets. As we continue to explore the farthest reaches of space, the mysteries of dark holes will captivate our imaginations and drive scientific discovery. The implications of dark hole research extend far beyond theoretical physics, potentially influencing other disciplines such as technology, philosophy, and even our understanding of human existence. If dark holes hold the answers to the nature of space-time, energy, and matter, they could unlock groundbreaking advancements in energy harnessing, space exploration, and computational power. One area of intense focus is the relationship between dark holes and quantum mechanics. Physicists have long sought a unified theory that reconciles quantum mechanics with general relativity, two foundational but seemingly incompatible theories of physics. Dark holes, as extreme regions of space-time where both gravitational and quantum effects dominate, offer a natural testing ground for this endeavor. Efforts like string theory, loop quantum gravity, and the holographic principle aim to bridge the gap, with some theories proposing that the universe itself might be a holographic projection encoded on the surface of a vast cosmic boundary, much like the event horizon of a dark hole. Additionally, the study of Hawking radiation has raised profound questions about the nature of entropy and information in the universe. If information is not lost in a dark hole, but rather encoded on its surface or emitted through radiation, it could mean that space-time is far more structured and interconnected than we ever imagined. This realization challenges our deepest assumptions about causality, determinism, and the arrow of time. Philosophically, the notion that we might exist within a dark hole or a simulated universe forces us to confront existential questions about reality and meaning. Are our perceptions merely a shadow of a more profound, inaccessible truth? What would it mean to discover that our universe is but one bubble in a vast multiverse, with dark holes acting as gateways between dimensions? These questions are no longer confined to the realm of metaphysics. They are now at the forefront of scientific inquiry. The James Webb Space Telescope, alongside other advanced observatories like the Event Horizon Telescope, continues to push the boundaries of what we can observe and understand. Recent images of dark holes, such as the first-ever photograph of the supermassive dark hole at the center of the M87 galaxy, have given humanity a glimpse of these enigmatic objects. As technology improves, we may one day gather enough data to create detailed models of the processes occurring within and around dark holes, providing answers to questions that have eluded us for centuries. Beyond the scientific and philosophical implications, dark holes also serve as a source of wonder and inspiration. They remind us of the vastness of the cosmos and the limits of human understanding, encouraging us to dream, explore, and question the world around us. As Carl Sagan once said, somewhere, something incredible is waiting to be known. Perhaps dark holes are the gateways to that incredible unknown. In conclusion, the study of dark holes stands at the intersection of science, philosophy, and imagination. It challenges our understanding of the universe, pushes the boundaries of human knowledge, and compels us to question the nature of existence itself. As we continue to unravel the mysteries of these cosmic phenomena, we may not only discover new truths about the universe, but also about ourselves. The journey into the depths of a dark hole is, in many ways, a journey into the depths of human curiosity and ingenuity. A journey that promises to reshape our understanding of reality and expand the horizons of possibility.